The transformer architecture truly reshaped how we build models, especially with this paper, Attention is All You Need. It makes a bold claim right in the title.
That's a strong statement. Before this, I thought recurrence and convolutions were fundamental for sequence and spatial data. What problem did it aim to solve?
Exactly. Previously, for tasks like machine translation, the dominant sequence transduction models relied on complex recurrent or convolutional neural networks. They were effective but had limitations.
I remember those. RNNs struggled with very long sequences, and CNNs were often localized. How did the transformer offer a different path?
The authors proposed a radical shift. They state, "We propose a new simple network architecture, the transformer, based solely on attention mechanisms." This was the core idea.
Solely on attention? So no RNNs or CNNs at all? That seems like a huge departure from the established approaches at the time.
Yes, dispensing with recurrence and convolutions entirely. This was a key part of its elegance and power. In case number TCM033002, we touched on this generalization.
But how does it process sequences without recurrence? Doesn't that lose the order of things? I'm picturing scrambled words.
That's a crucial question, Maya, and it's addressed by positional encodings, which we've covered before. A major advantage of ditching recurrence was that it became more parallelizable and requiring significantly less time to train.
So the computations for each part of the sequence could happen simultaneously. That explains the speedup, but the accuracy still needs to be there.
It certainly was. The transformer achieves 28.4 blue on the WMT 2014 English to German translation task, improving over existing models. This wasn't just faster, it was better.
So faster training, better results. That's a compelling combination, especially for a new, simpler architecture. It shows attention truly is powerful.
And not just translation, they showed it generalizes well to other tasks by applying it successfully to English constituency parsing. This hinted at its broader applicability.
So it's not just a language model-specific trick. This attention is all you need idea seems to mean attention is a universal building block. How does it actually work?
That's the core question we'll tackle next. We'll break down the mechanism of self-attention step by step, building on some concepts from case number TCM063003 about bidirectionality.
Good. I'm ready to see how this solely attention model takes inputs and learns to understand them.
We've established the transformer's impact. This illustration describes it as a model that uses attention to boost the speed with which these models can be trained. So how does it do that?
We saw the more parallelizable claim earlier. I'm looking for the how behind that and what self-attention truly means.
At a high level, the transformer maintains the encoding component, a decoding component, and connections between them, similar to earlier sequence-to-sequence models.
Okay, so the overall shape is familiar, but the internal workings must be very different without recurrence or convolution.
Indeed. Within each encoder, the encoder's inputs first flow through a self-attention layer. This is where the magic happens for understanding context within a single input sequence.
Self-attention? It sounds like a word looking at itself, but why would it need to? How does it help it process other words?
Consider the sentence, "The animal didn't cross the street because it was too tired." To understand it, self-attention allows it to associate it with animal.
That's a great example. So self-attention lets the model dynamically weigh the importance of other words in the input sequence when encoding a specific word.
Precisely. It bakes the understanding of other relevant words into the one we're currently processing.
Think of it as a smart lookup, like searching the library for books on a topic, but more profoundly, it's learned interpolation. Unlike a simple lookup that returns specific items, self-attention dynamically blends information from all relevant books, other words, based on how strongly they relate to your query, the current word, creating a new, enriched summary or representation.
So it's not just a memory, but an active, context-aware blending. That clarifies a lot. How does it achieve this dynamic weighting?
The first step is to create a query vector, a key vector, and a value vector from each input word's embedding. This is done by multiplying the embedding by 3 learned weight matrices.
Query, key, value. These sound like database terms. A query to search against keys and retrieve values?
That's a good analogy for the conceptual roles. Think of a query as what you're looking for, keys as what's available, and values as the information associated with those availabilities. However, in a typical database, a query either matches a key exactly or not, returning a specific value. Here, every query compares against every key to get a soft match, a score, and then we take a weighted average of all values, rather than retrieving just one or a few discrete ones. It's a continuous, blended retrieval. The score is calculated by taking the dot product of the query vector with the key vector of every other word. This dot product measures similarity or relevance.
So, my query for it would be compared to the keys of animal and streets, and whichever has a higher dot product gets a higher score. That makes sense.
Next, we divide the scores by 8, which is actually the square root of the dimension of the key vectors, dk. This scaling is crucial because without it, as dk increases, the dot products can become very large in magnitude. Large values can push the softmax function to regions where its gradient is extremely small, leading to vanishing gradients and making training unstable. After scaling, we then pass the result through a softmax operation. This normalizes the scores into probabilities that sum to 1, representing the attention weights.
So now I have a set of weights indicating how much each word should attend to every other word, including itself. That's the learned interpolation you mentioned.
Precisely. The 5th step is to multiply each value vector by the softmax score. This scales the value content of each word by its learned attention weight.
And then I assume these scaled value vectors are combined to form the final context-rich representation for the current word?
You've got it. The final step is to sum up the weighted value vectors. This produces the output of the self-attention layer for that position. This whole process happens in parallel for all words.
Okay, that's incredibly clear. The parallel nature of QVK dot products and weighted sums really enables that speed we discussed. But could this work for something totally different, like images?
That's an excellent lead-in to our next section. We've built the mental model for how self-attention processes sequences. Now let's see how that generalizes to computer vision.
I'm curious how attention is all you need holds up when pixels are the input, not words.
By 2020, the transformer architecture has become the de facto standard for natural language processing tasks. Yet, as this paper notes, its applications to computer vision remain limited.
I see. We've seen how powerful it is for text, but vision has typically been the domain of convolutional neural networks with their spatial awareness.
This paper, titled "An Image is Worth 16 by 16 Words," challenged that. It stated reliance on CNNs is not necessary, and a pure transformer applied directly to sequences of image patches can perform very well.
A pure transformer? No convolutions at all? This goes against the common wisdom that convolutions are essential for understanding local image features.
Their key insight was treating an image not as a 2D grid, but by breaking it down. They showed the transformer could be applied directly to sequences of image patches.
So you chop up the image into smaller squares, flatten them into vectors, and then treat each square like a word in a sentence?
Exactly. You treat each square like a word in a sequence. Where this analogy stretches, though, is that unlike words, which have inherent semantic meaning and a relatively fixed vocabulary, these image words are just raw pixel patches. Their meaning and relationships are entirely learned from scratch by the transformer, rather than leveraging pre-existing linguistic structures. Also, words have a natural linear order, whereas image patches have 2D spatial relationships that positional encodings need to capture. The title, "An Image is Worth 16 by 16 Words," refers to this.
That's a clever abstraction. It reframes the image data to fit the transformer's native sequence processing capability, just like we discussed in case number TCM 153005.
And it worked. The Vision Transformer, VIT, attains excellent results compared to state-of-the-art convolutional networks on various benchmarks, like ImageNet.
So not only is it possible, but it actually competes with or surpasses the specialized vision architectures. That's truly remarkable versatility.
That's incredible. But does this approach have any practical downsides or specific requirements compared to traditional CNNs?
It does. One key assumption for VIT to truly shine is data scale. The original paper found VITs typically need pre-training on very large datasets to outperform state-of-the-art CNNs. Without that massive pre-training, CNNs, with their built-in inductive biases for locality, often still have an advantage on smaller datasets. Also, the computational cost of vanilla self-attention scales quadratically with sequence length, which can be demanding for very high-resolution images. This is hinted at when the paper mentions when pre-trained on large datasets as a condition for excellent results. This journey from language models to computer vision highlights the power of abstraction in AI. The transformer's core mechanism isn't about words or pixels, but about relationships within sequences, a truly elegant solution. And it shows that sometimes the most groundbreaking insights come from questioning established wisdom and finding universal principles. Attention is all you need indeed.